Hello students, my name is Shashank Shekhar and today is the 8th lecture of the chapter, that is Haloalkane and Haloarene. So if you attended the previous class, you must have seen that we have covered all the reactions and properties of this haloalkanes. Now today we'll move to haloarenes. So similar to this haloalkane, we will today see first of all this nature of the CX bond, that whether this CX bond is good for this nucleophilic substitution or not. So we'll see this. So today I will mainly focus on why this nucleophilic substitution is not good for this haloalkane, and second, in what condition it can go this nucleophilic substitution. We will see that part. So if you look at the syllabus here, so we have covered this part, that is the nomenclature. We have seen the nomenclature of both haloalkane and haloarene in one. After that, we have seen the nature of CX bond for haloalkanes. Then we have seen the preparation, physical properties, chemical properties, and the stereochemical aspect of your substitution reaction. So up till this part we have covered. Talking about this class, we will mainly be focusing on the nature of CX bond, and we will be studying one type of substitution reaction, that is the nucleophilic substitution reaction. Now coming to the topics that we will cover under this chapter, under this nucleophilic substitution is this. First, we will see what is nucleophilic substitution and what are the reasons it does not undergo, or the haloalkane does not undergo nucleophilic substitution, starting from resonance effect, then difference in hybridization, repulsion from electron clouds. After that, we will see some reactions that are exceptions to these conditions and show nucleophilic substitution. So the first one is the replacement by hydroxyl group. And secondly, we will see the mechanism of this nucleophilic substitution, how this haloalkane is going under nucleophilic substitution. So coming to this nucleophilic substitution, so first of all, you must understand what is nucleophilic substitution. So nucleophilic comes from the word nucleophile, which means nucleus plus philic, okay, means nucleus loving. Now nucleus, what is the charge on nucleus, or what is nucleus? Generally nucleus is positively charged. So if a species or a chemical ion or something like that is loving, or you can say is being attracted towards positive charge, then that species is termed as your nucleophile. Now if a nucleophile is substituting your your derivative, then we will say that it is nucleophilic substitution. So in this case, the thing that is to be substituted is the halogen, since we are talking about haloarenes. So basically we will see a nucleophile substituting our halogen, that is nucleophilic substitution. Now in general, these aryl halides, all the haloarenes, are not that much reactive to your nucleophilic substitution due to 4 reasons. We will go through these reasons one by one and see what are these. But in some harsh conditions, or you can say for some special derivatives of your halogen or haloarene, this compound can go your nucleophilic substitution. We will see those derivatives, plus we will see those harsh conditions. So if by harsh condition we mean that by heating or by using your concentrated acid or something like that. Okay. Now the factors that are responsible for this less reactivity of this towards nucleophilic substitution of this aryl halides is first one is resonance effect. Second one is difference in hybridization. Third one is instability of an alkation, and fourth one is repulsion from pi electron cloud. We will see each of these one by one. Okay. So for the note, you can keep it in mind that okay, I will give you some substrate that will only undergo your nucleophilic substitution and others not go. So you will not be seeing those reactions which undergo nucleophilic substitution. Suppose you have a nucleophile like OH minus, and that cannot replace your Cl minus, but under some harsh condition it can undergo, but under normal condition and for simple derivatives of your chlorohaloarenes, it cannot give your nucleophilic substituted products. Now what are the factors that are responsible for this outcome? Well, the first one is resonance effect. So you are aware about this resonance. First of all, you must be having a good idea about this resonance. Now if you look at this compound here, this chlorine here has a lone pair. So the same thing is written here, that the electron pairs are present on halogen atom. and this lone pair are in conjugation with the pi electrons of your benzene ring. Okay, this is our benzene ring, and there are 6 pi electrons, 1 2 3 4 5 6, and here is our lone pair. Now you can see that this lone pair are in conjugation. Conjugation means they both are moving. You can say that like this can move here due to the movement of this electron. I would say that this can move here due to the movement of this electron, or you can use a more simpler word, that is delocalization of electrons. So this lone pair are delocalized across the ring. Now due to this reason, if you see one of this resonance structure, then it is not having a double bond, but other three, these three are having carbon chlorine double bond character. You can see here very clearly. You can see it very clearly that here CCl bond has a double bond character. Now you know it very well that a double bond is very reluctant towards your say this breaking of bond as compared to a single bond. Means double bond cannot be broken easily as compared to single bond, because now the bond length is shorter, okay, and your bond order is also high. Now due to this reason, they do not undergo nucleophilic substitution reaction. So this is one of the reason, that is resonance effect. So it is written here also very clearly that the bond cleavage in haloarene is difficult than haloalkane, and therefore they are less reactive towards nucleophilic substitution. And the reason is the CCl bond acquires a partial double bond character due to resonance. So after resonance, this lone pair is moving here, and this pi bond is moving on this carbon. Okay, this pi bond is moving on this carbon, due to which we see a double bond character here. Similarly, in all of these three, we have a double bond character. So this is the first reason, that is the resonance effect. Now the second one is difference in hybridization. Difference in hybridization. So in haloalkane, the carbon atom is attached to in sp3 hybridized, while in case of haloarene, the carbon atom is attached to sp2. Okay, so this point must be very clear. So if you look at a, say, your haloalkane, you can see that this carbon is sp3 hybridized, as it is making 4 bonds, while this carbon that is attached to halogen in case of haloarene is sp2 hybridized, because it is making only 3 bonds. So it is sp2 hybridized. Now this sp2 hybridized is not that much vulnerable to your substitution. Why is it so? So the question arises, why is it so? So this sp2 has a much more greater S character. So if you compare the S character of sp3 and sp2, so in sp3 this S character is 25%, whereas in sp2 the S character is 33.33%. Now you can see that in sp2 carbon the S character has increased, and now you know that the S character increase means your electronegativity had increased. Your electronegativity had increased. So why I am saying this? If you know the concept of hybridization, the thing which I mean here is that the S character is more, means the molecular orbital, or you can say the orbital, not the molecular orbital, the hybridized orbital that has been formed by the combination of your 2 p orbitals and 1 s orbital is resulting in a say hybridized orbital which has more S character. And if you know that this S orbital is more towards your nucleus due to an equal amount of pull from all sides, as it is, say, your spherical in shape. Okay, this is clear. Now since it is more attracted towards your nucleus, that means this orbital has a greater electronegativity. See, if you are taking something from something, suppose this is your molecular orbital. Okay, your molecular orbital has been say under the influence of your carbon. Okay, your say your orbital sp2 orbital is under the influence of your carbon, and since it is having more S character, therefore its electron has been removed. So it is kind of electron deficient now, and since it is electron deficient, if it will look for more electron, And that is the only definition of electronegativity. So since we are making this, say your orbital, hybridized orbital, sp2 hybridized orbital more electronegative, therefore it will attract your halogen with a greater force. It will attract your halogen with a greater force, or it will held tight this halogen. Due to this, it is difficult for your cleavage of this C and X bond. So it is difficult. It becomes difficult for cleaving this C and X bond. Now this can be seen with the help of your bond length also. So if you see at the CCl bond length of haloalkane, it is 177, while in haloarene it is 169. So you can see there is a difference of, say, your 8 picometer. Okay, so it is 8 picometer shorter than your CCl bond in haloalkane, this haloarene. And what is the reason behind it? The reason behind it is hybridization. Okay, the reason behind it is hybridization. Therefore, it is difficult to, that it is difficult to break a shorter bond at a longer bond. Therefore, haloarenes are less reactive than haloalkane towards nucleophilic substitution reaction. Now, for this, you have to think of two possibilities. First possibility, we know that, okay, SN1 and SN2. Second one is SN2. So a nucleophilic substitution can go either through the three ways, I would say. But since there is no possibility of the third way, that is SNI, so we will just focus on SN1 and SN2. Now you know that SN1 requires breaking of your CX bond. Okay, SN1, because the CX bond breaks and we get a ionic species. And going to your SN2, the nucleophile attacks and the leaving of the X group occurs simultaneously. Now for both of this, the breaking of this bond of CX is important. And the both of the factor we have seen earlier is, you can say, in a way, not allowing to break the bond between C and X. So therefore, both of these mechanisms, that is SN1 and SN2, are violated, or you can say prohibited. And therefore this haloarene cannot undergo nucleophilic substitution. So these are the two reasons. The third reason is instability of phenylcation. Okay, instability of phenylcation. Suppose your species or your haloalkene is going nucleophilic substitution by SN1 mechanism. SN1 mechanism means what? First, the halogen will leave by itself to form your cation. But this cation is not stable. This phenylcation is not stable. Why is it so? Because now this has made your system less aromatic. Okay, this has made your system less aromatic. How? Because now the electrons will find it more difficult for conjugation. So this has kind of reduced the aromaticity of your phenyl group. Due to this reason, it cannot go your SN1 reaction. Therefore, we can make a statement that since the formation of your phenylcation is difficult due to its instability, therefore it cannot go SN1 reaction. And SN2 requires the attack of your nucleophile and breaking of bond at the same time. The previous two reasons you have seen were both for SN1 and SN2, as it was regarding your cleavage of the C and X bond. But in this case, we are studying them equally. So if you are going through SN1, it cannot go SN1. Why? Because the phenylcation would be unstable. Now suppose it is going through SN2, but for the nucleophile to attack, it must acquire a positive charge. So if you have studied this aromatic system properly, you must know that there is electron cloud. So these both are, sorry, let me show it with a different one. So this both are electron clouds. This one and this one. They both are electron clouds that is surrounding your carbon atom, which is to be attacked by your nucleophile. Okay, which is to be attacked by your nucleophile. Now, if a nucleophile comes, it will experience repulsion. Why? Because your nucleophile is kind of carrying a partial negative or a complete negative charge. Then and then only it will attack electrophile. Now, since it is carrying a negative charge and your electron cloud is present on your phenyl system, therefore, this nucleophile will find it difficult to attack on any of these carbon, including a carbon containing chlorine, because the repulsion it experiences from your electron cloud. Due to this reason, it will not go SN2 either. Okay, SN1 it will not go because the phenylcation is not stable. SN2 it will not go because you are having electron cloud that will repel your coming or incoming nucleophile. So is this clear? So this is the thing. So these are the four reasons which I have discussed just now, that is responsible for prohibition of this nucleophilic substitution reaction. But you will see that in some cases, or for specific derivatives of your halogen, this can go nucleophilic substitution. Now we'll see all those reactions one by one. So basically there are 3 to 4 reactions. I will show you more examples in the next class, but for now I will just give you a glance, or you can say overview of what a nucleophilic substitution looks like in your haloalkane system. So let us see some reactions for that. Now this is the first example of your nucleophilic substitution of a haloarene. Here you can see that we have converted our chlorobenzene to phenol. But if you look at the conditions here, we have used really harsh conditions. So basically, we have used your aqueous NaOH at 623 Kelvin. 623 Kelvin means if you subtract 623 from 273, you will get 12 minus 7, 5, 5 minus 2, 3. So you can imagine how high this temperature is. It is 350 degrees Celsius. Okay, 350 degrees Celsius is really a high temperature. So if you want to imagine what is 350 degrees Celsius, you start sweating, or you started feeling hot at 40 degrees Celsius, and 50 degrees Celsius is very hot. It is like in your western part of India. So imagine what a high temperature is to be given to this haloalkane to undergo nucleophilic substitution. So by the high temperature, you can imagine the level of, or the extent of harsh condition that is to be applied on a haloarene. And plus you have to give high pressure also, 300 Kelvin, 300 atm. So this is very high pressure. So if you don't know, that 1 atm pressure is your normal pressure that you feel in the environment. So it's the 1 atm pressure that is present around you. So 300 times greater pressure has to be applied. So a higher temperature and a greater pressure both are to be applied to do this nucleophilic substitution. Now if I do the first step, then the formed product would be this. Okay, and after that we will do the protonation with the help of H plus to get our final product. So remember this method, it can be used for a preparation of phenol. When you will study your phenol, or you can say alcohols and phenols and ethers, then you will see this reaction again. But remember the conditions also. You need aqueous NaOH in presence of high temperature and high pressure, extremely high pressure and high temperature. After that, we will protonate our substrate to get our final product, that is phenol. So this is a kind of nucleophilic substitution. How? Your OH minus is coming, which is a nucleophile because it has an electron or a lone pair, and it is negatively charged, so it will be a nucleophile as it will be attracted towards your nucleophilic substitution, or you can say nucleophilic site. Now, although of the various reasons, this carbon Cl bond is not that much polar, but okay, it has some polarity. Why? Because of the nature of CX bond, that is the chlorine is electronegative and carbon is electropositive. Now at high temperature and pressure, it will attack this point and this Cl will be left out. So it has a different mechanism. So it goes like this and it is kicked out. Okay, it goes in this fashion and we get our OH here at chlorine position. So here a nucleophile is substituting, therefore it is a nucleophilic substitution. So this is one of the example. Now similar to this, we can have more examples. So here I have given some more examples. Now these examples are very important. What we are doing here. So if you see here very carefully, you can see that our main compound is same. We have just used the derivative of your chloroarenes. Okay, this is our chloroarene, this is our chloroarene, and this is our chloroarene. What we have done, we have started to substitute it one by one. First of all, we have substituted para position of your chloroarene or haloarene. Okay, then we see that okay, in the first one we require high pressure and high temperature, but here we only need high temperature, and that is not also that much high. So if you just try to find in terms of Celsius, so why I am doing it in Celsius, because it will make some sense to you. So you are more aware about your degree Celsius rather than your Kelvin. So I am using this conversion, that is 11 minus 14 minus 7 and 3 minus 2 1. So it is 170 degrees Celsius, which is much lower as compared to your normal chloro derivative, which is having no nitro. And we do not require high pressure also. In the next reaction, what we do, we introduce one more nitro. Like here we have introduced at this position, we have introduced one more nitro. Again, this will make your nucleophilic substitution easier than the previous one. Now we know, now we have to give a lower temperature as compared to this one. So if you subtract this one, 835 1679, it is 95 degrees Celsius. So you can see what a drastic change has been brought by introducing one substituent. Plus it will not require pressure also, and we just put H plus. Now look at the third one. It is very interesting. If you put 3 nitrobenzenes here, okay, sorry, 3 nitro derivative nitro groups here, then you just have to pour warm water. Warm water, that is you can just imagine as lukewarm water or something like that. You have just to pour this warm water, and your product will be formed, or your nucleophilic substitution will be done. So we have replaced your Cl with OH. So these are the 3 examples. Look at it carefully. You will notice that as we are introducing your NO2 group, the nucleophilic substitution becomes easier and easier. So in the introduction of 1 nitro, we require lower temperature and no pressure. At the introduction of 2 nitro, we require an even lower temperature but no pressure. And at 3 substituent, we do not require very high temperature. We just need some warm water, and it will easily convert your chloro derivative of 2,4,6 nitro. 2,4,6 dinitro-chloro in this 2,4,6 dinitrophenol. So it is also termed as 2,4,6 DNP. You will use this, or it is a test, 2,4,6 DNP test. You will use this. Okay. So it is a very good method to prepare your 2,4,6 DNP. So keep this reaction in mind. This is very important. Okay. So what does this DNP stand for? 2,4,6 dinitrophenol. Okay, sorry. So it will be trinitrophenol. 2,4,6 trinitrophenol. So I will check this name again. So it is phenol, and at 2,4,6 position we have our nitro group. So here also we have replaced your Cl by OH. Okay, in this case also, and in this case also. This is clear. Now we will see the mechanism of how it is happening. So I have just given you a glance of it in the previous slide, that how it is happening, but we will see the detailing of it. Okay, that would make your sense more clearer about how this reaction is going on. So let us look at the mechanism now. Okay, so this is the mechanism. So it may look very cliche to you, or you can say very clumsy to you, but I will explain it, and you will see that it is not that much difficult to go through. Now we have seen that this NO2 group introduction has done some easiness to your substitution, nucleophilic substitution reaction. Okay, so we have seen this. So as we introduce more number of nitro group, we will see that this nucleophilic substitution becomes easier and easier. However, this reactivity is more pronounced in case of ortho and para as compared to meta. Okay, so this is more seen, means the reactivity increase is more pronounced in case of ortho and para as compared to meta. We will see what is the reason behind it. So for that, let us look at our mechanism first of all. So this is our nucleophilic substitution reaction. So first of all, this OH here is attacking at this part. Now due to this pi electron is moving on this carbon. So you can see here, this is the movement here, it is shown. Now this pi electron, the negative charge, moves here on this, between this and this carbon, and again this pi electron, this goes on this carbon. In the next part, this pi electron moves here, and again this goes on this carbon, and at last this negative charge comes here at back and it kicks out your chlorine group. Now if you want to draw the resonance hybrid of all of this, so basically our structure is this, and this is our resonance hybrid. So you can see that this negative charge is being circulated through all of this carbon atoms except this carbon. So this circle is left open here, okay, because this carbon is not is taking part in your delocalization. Is this clear? Now this is the slow step because this attack is very much defended by your pi electron clouds and your partial carbon partial double bond character and all of those. Therefore this slow step and it's very difficult to follow through. Now this removal of Cl is very fast. Why is it so? Because it is regaining its aromaticity. You can see here a kind of aromaticity has been disturbed because now this carbon is not taking part in conjugation. Therefore there is not complete conjugation. As a result, it is becoming non-aromatic from going from here to here, but going from here to here makes it back your aromatic. Therefore this step is slow and this step is fast. So as soon as this comes here, this Cl leaves and we get our product. Now what is the function of your NO2 group here? So you can see here very clearly that the negative charge is being formed as this position, and this position. Okay. Now this NO2 group is kind of electron withdrawing. Now this negative charge can be stabilized by your nitro group more at ortho position. Why? Will see why. Okay. But just for now, assume that okay, this negative charge is being stabilized by your electron withdrawing group. Similar to that, if I have a say ortho substituted nitrobenzene, okay, ortho substituted nitrobenzene, sorry, chlorobenzene. Now again OH minus will attack here. This will again rotate through all of these and we will again get the same resonance hybrid. Here also the NO2 is present and it is, say, you're stabilizing your negative charge that is moving through the ring, and at last the Cl is kicked out and we get our product. The same thing goes with the meta. We again have a negative charge here which moves or cycles through all of this ring, and at last it is kicking out your Cl group. Now what is the difference? I would ask you that what is the difference between this these two reactions and this reaction? What is the difference between these two? So if you remember that this nitro group is kind of electron withdrawing group. Now you remember that this negative charge was developing here and here and here when we have attacked our OH group. Now if you remember the resonance structure of your NO2 nitrobenzene, it happens like this. Okay, it goes like this. Although it is stabilizing through inductive effect, it will also stabilize through your resonance effect. So we'll see how. So this is your, say, electrons. Now you say that we are developing negative charge here. Okay, we are developing negative charge here. Now what will happen? What will happen as a result of this? It will go here and it will kind of go here, and this will be delocalized on nitro group also. Now you can see that this negative charge is not only being delocalized through the ring but also on the nitro group. If your nitro is para to chlorine, then only. In that case only. Similarly, if you consider the ortho part, here is a chlorine. Okay. Now this chlorine developed negative charge here also. Now this negative charge can again be delocalized on this nitro group. So in both these cases, you can see that the negative charge that has been created due to attack of your OH is being, say, neutralized, or you can say delocalized by your nitro group. And this is the reason the negative charge is more stable, or you can say the reaction is more favorable in case of ortho and para as compared to meta. So if you see meta, so it looks like this. So there is no development of negative charge on this part. Okay. So negative charge only develops here, here, and here. And this is the reason why as the introduction of nitro group increases, your nucleophilic substitution goes easier and easier, because now the negative charge is been delocalized by 3 nitro at groups. Then in down we have 2 nitro groups, and the least one is 1 nitro group. Now is this clear that why is this stability of say, or you can say the reaction of ortho and para is more than meta? Okay, so it's clear. Now here you can see very clearly that the negative charge develop here, here, and here. But this negative charge is not say propagated to your nitro group, or it cannot be propagated to your nitro group. Okay, it would go your nucleophilic substitution, but not at much faster rate as this ortho and para are going. Now it is very important to look at this resonance structure also. So you must notice this one, that this is open from one side. Each of this is open on one side, because the negative charge here is only being delocalized on the 5 carbons and not on the 6th carbon that is containing both chlorine and hydroxyl. Is this clear? Okay. So due to this reason, we get a ring open here. And since the negative charge is delocalized, therefore we put a negative charge here. So this is the mechanism for nucleophilic substitution. So if I put all these reactions in a nutshell and all the concepts in a nutshell, then I would say that our haloarenes do not undergo nucleophilic substitution very easily, or they undergo nucleophilic substitution only some harsh condition or for some special derivative. Now what is the reason behind it? The reasons are very clear. The first one was resonance hybrid. The first one was resonance, which was creating a partial double bond character between carbon and halogen. The second one was your nature of your CX bond. The first one was resonance. The second one was difference in hybridization. Since they both are different in hybridization, because your simple haloalkane is sp3 hybridized and it is having less s characters compared to haloarene, which is sp2 hybridized and has a more s character. So since it has a more s character, therefore it is pulling your halogen more effectively. So third reason, what is the third reason? The third reason is that instability of phenylcation. The first two reasons are both for SN1 and SN2, because both of this reaction involves breaking of your carbon and halogen bond. But if you move to SN1 and SN2 specifically, then the first one, that is SN1, goes through formation of your phenylcation, while your this SN2 goes through breaking of bond and making of your say nucleophile and carbon bond at the same time. So if I go for SN1, then it would result in the formation of your phenylcation. So since the phenylcation is formed, it is not that much stable because it is disturbing the aromaticity. Therefore, SN1 is not possible. Now the second one is your say electrophilic or nucleophilic attack of SN2. So you know very well that the electron cloud is surrounding the carbon that is to be attacked, and these electron clouds are negatively charged. Okay, these electron clouds are negatively charged. So since the electron clouds are negatively charged, therefore we will this incoming nucleophile will experience, this incoming nucleophile will experience repulsion from your, say, electron cloud. Okay, this is clear. Okay, now these are the 4 reasons it will not undergo nucleophilic substitution. Now we'll next move to, we have next moved to your some special conditions in which the nucleophilic substitutions occur. The first one was chlorobenzene. So in chlorobenzene, what happens? This chlorobenzene undergo nucleophilic substitution under harsh conditions. And what are those conditions? The first is the high temperature, and the second one is your high pressure, and very high temperature, I would say. And the pressure is 300 times than the atmospheric pressure. Now, due to this reason, this can undergo nucleophilic substitution. Now, the first one is the harsh condition, and the second one is your for suitable substituent. So, if you substitute it with a suitable substituent like nitro group, suppose you have put a nitro group at your para position or your ortho position, then it would be more pronounced due to the reason I have told you. And if you keep on increasing the number of nitro groups, then you will see the nucleophilic substitution becomes easier and easier because of the stabilization of the negative charge that is being dispersed to your ring. So we have seen that as we introduce more number of your nitro group, we get our nucleophilic substitution more easier and easier. And at last we introduce 3 nitro groups, and by just putting hot water we get our final product, that is 2,4,6 DNP, 2,4,6 dinitrophenol. So this is about the nucleophilic substitution. So with this I would like to end my class. Now in the next lecture, what we will see some electrophilic aromatic substitution. So this is the most important part, I would say. So we will go through various reactions and we will see what is the effect of derivatives of this, or you can say what is the effect of substituent on your electrophilic aromatic substitution. So it is also termed as EAS, electrophilic aromatic substitution. So with this we would end our haloarenes. And one more thing we will discuss here, important thing that is sometimes asked in exams, and I would say this is important. So some commercial products which are some commercial halogen or haloarenes that are important for the daily life. Okay, so I would like to now end my lecture. Thank you.